All right, welcome everyone. There are two sheets you picked up on the way in. They are also linked in Canvas under today's agenda. So modules, class, the week of, oops, I forgot to put the week of, but Monday the 20th is today. So there's three things in there. One of the things we're about to go through is a slide presentation, but the other two is the exploratorium and then this study guide. So the exploratorium is we're going to look at some properties of water. This properties of water exploratorium is for you to get a basic understanding of some unique properties of water. All right, so on these, the exploratorium, there's some properties of water that we are going to talk about, and you're going to go around to some stations that you will have, will be using kind of throughout the year. That is not directly going to be on your test. That is on Wednesday. Your test is Wednesday, test is Wednesday, your test is Wednesday. One of the packets you picked up is a study guide. The study guide is an assignment that I'm going to have due for tomorrow. It's another kind of emphasis on the content that you'll be evaluated on. There's a Google Doc version, there's a PDF version, there's a paper version that you have. I do want to show you that on a study guide right here is the answer key. So I did give you all the answers, so hopefully you'll realize that getting the answers is not the important part of this task. The important part is for you to understand and make sure you know this. So, but it does provide you with the opportunity to check your work and also make sure you're on the right track. So if you note right here, there is a link that would get you to your answer key. This is due tomorrow night by 11:59 p.m. Okay. The next thing we're going to talk about is we are going to talk about water. When we are in biology, we talk about life. Science is trying to find or understand phenomenon. Biology specifically is, you break the word down into its two roots, is the study of life. Life as we know it is often how scientists will say it. Life as we know it requires water. All living things that we know of, life as we know it, need water either to live or they originated from water. So when astronomers or astrophysicists, I should say, I don't know, I guess technically who's searching, but when we're looking for life in other planets or other galaxies or other solar systems, we aren't looking for life, we're actually looking for water first. And if we find water, then we can kind of follow up, well, is there some life forms that once existed on some level at some point? So they look for water first because life as we know it is how they say it. Needs water. Now, with new evidence, that could change. There might be some life that doesn't require water or never did require water, but as we know it, it does here on Earth. So, in today's agenda, there's a link to a set of slides. We're going to start on slide 5. There's nothing for you to fill out or notes for you to take on this. These are just some general kind of properties of water and some notes about water that we're going to be kind of using throughout the year. There's, when you do the 6 state, or there's 9 stations that we're going to look at today in class. They're going to ask which property of water. They're on the board. They're also on the slides. If you are working, you say, hey, I remember there was that slides about water. I just don't remember what the properties are. Today's agenda, Monday, September 20th, there's a link to this slide presentation. We started on slide number 5. So water is important for life. Water has some unique properties, and one of the properties is water is a polar molecule. And polarity refers to when electrons are shared with the bonds, but they aren't shared equally. So hydrogen and H2O is what we chemically refer to as water, is they share, but the electrons spend more time around the oxygen than they do the hydrogens. So because of that, we get a charge. Partial negative and a partial positive charge. That's what these little squiggly lines refer to a partial. But this is a negative charge on this end. These are positive charges on this end. Water is a charged particle. It has positives and negatives. And like a lot of things in nature, like charges repel and opposites attract. So with water molecules, because they are charged, when they are near each other, they also arrange in that pattern where opposites attract and like charges repel. So with water, it's a specific type of bond called a hydrogen bond, where this negative, positive end of hydrogen is attracted to the oxygen is attracted to this hydrogen, and they arrange in a certain structure, in a certain way. And a hydrogen bond is a very weak chemical bond, but we have enough of these very weak chemical bonds that it makes it significant. And it's a strong enough bond that it has an impact, and it affects things in nature and in life. And it's because of these unequal sharing of electrons. Okay? So, a lot of these properties of water, the 6 that are listed here are also listed on the board, have a lot to do with this hydrogen bonding and how water molecules are attracted to themselves or other things because of these charges. So when we talk about water, one of the things has a high boiling point. So we use the Fahrenheit system here in the United States. The rest of the world say water boils at 100 degrees Celsius. We would say it boils at 212 degrees Fahrenheit. But it's relatively high compared to like methane and oxygen and hydrogen gases. And if you think of oxygen, I breathe in air which has lots of other things in it, but oxygen is the big one that we care about. And oxygen has already boiled. Right? If something's in the gaseous state or the gas form, it's already boiled and it's in the air. So is there such thing as liquid oxygen? Yeah, it's just really, 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 really cold. And it boils, and when it boils, it becomes the gas form. Periodic table has lots of different elements on there. The black elements, these are pure elements, not compounds or molecules. But the black molecules, the letters that are written black, are solid at room temperature. The blue ones are liquid at room temperature, and the red ones are gas at room temperature. Okay, so those red ones in the upper right-hand corner, they're like right now, they would be in the gas form. There's 2 that are in liquid form, bromine and mercury, but the rest are in solid form. Now the ones with like the white letters, those are man-made, artificially made. So those are what those are. But it has a fairly high boiling point. And this is important because it has an impact where a lot of life needs liquid water. So even when things get really warm, like a hot sunny day, water sitting in in a shallow pond, it didn't boil and like cook the organisms in it. Water has a pretty high specific heat value, and that's something that's pretty important to maintain something called homeostasis. And homeostasis is an organism's ability to maintain like an internal balance. So we have a body temperature is a pretty good example of that. We're at like 98.6 degrees, give or take. About 98.6 degrees. And what happens if your body temperature gets below that a couple degrees? What do we call that when your body temperature gets too low? Hypothermia. And what happens if you don't do something about hypothermia? What happens if you're hypothermic too long? You shut down and you die. Okay, you die. Okay, what happens if you get too hot? You overheat. You get they talk about like a high fever. Some of your organs start to shut down and you die. Okay, we have a couple degrees each way that we're good at. Anything beyond that, we start getting in trouble. So your body tries to maintain a relatively constant body temperature, and we do things like shivering to warm up. We sweat to try to cool down. But most of our body is made up of water. It's also pretty important in terms of life and kind of buffering. If you think about the specific heat, specific heat is just saying like how much energy does it take to change the temperature of a given amount of a substance, a certain temperature. So they often talk about 1 gram of something 1 degree Celsius. So how much energy does it take? So the idea is if you took equal masses of water and steel, and you say, well, which one takes more energy to heat up? It's water. But it also retains heat better, so the water's going to hold on to that heat. So our lake temps, even though it's like 80 degrees sometimes, we get some weird days in like March and April that it's 80 degrees outside, and the ice is off Lake Wausau. Does that mean the lake temps are in the 70s? No, right? And even if we had a week of 80 degree temperatures, does that mean our water temps are going to be in the 80s? No, it takes a long time because it has to absorb, first of all, there's a lot of water, but it has to absorb that energy. It takes a lot of energy. Now, once it is warm in the summer and it starts to cool off, it also holds that heat. It holds it for a while. Okay? If you think of like Seattle, my sister-in-law lives in Seattle. So we've talked about like, well, how are the winters in Seattle? Because a lot of times we hear about rain and it's pretty rainy. And she's like, do you guys get snow? And she's like, yeah, we get some snow. I'm like, oh, you get a lot of snow? She's like, no, we get a little bit of snow and it lasts like a day or two. Maybe like last winter they had a weekend. It lasted a whole weekend. But that's not super common. And if you look at latitude, they're not, I don't think, too crazy different than we are. But why do they stay warmer than we do? Well, they got that giant Pacific Ocean not too far to the west. Now, they aren't on the coast, but they aren't too far from it. That has an impact because that retains a fair amount of heat, and the air blowing off of that ocean is going to be naturally warmer than if it wasn't there. The Great Lakes are a big enough body of water that they have an impact on the temperatures right along the lakeshore. So specific heat, it holds that water pretty well. Adhesion versus cohesion. Those are two different terms. It's one of those things, so you just kind of got to remember what one of them is, and then the other one is the other. So I remember adhesion because I can think of a Band-Aid. Now, Band-Aid is a brand name. The generic title of Band-Aid would be like adhesive bandage. Adhesive bandage. So I always think that like a Band-Aid adheres to your skin. It's two different substances, the Band-Aid and your skin, sticking together. And that's what's going on with water. When we talk about adhesion, water is sticking to something else. Okay, so it's sticking to like a leaf. Like, why aren't these falling? It's sticking to the leaf. Okay, it's clinging to the side of a graduated cylinder. Okay, we get the meniscus that's forming. We'll talk about that in a second. So adhesion is when water sticks to something else. It sticks to something else. Where cohesion is where it sticks to itself. So cohesion, they stick together. They stick together. So the morning, like rain droplets or dew droplets on a leaf, they bead together. The droplets stick together. At some point, you probably have tried to see how many drops of water you can put on a penny. You get this mounded effect like this. And like the penny itself is only like right here, but we were able to get quite a bit more water because the water is sticking to itself. Cohesion. And it all has to do with the polarity and that hydrogen bonding of the water molecules being attracted to itself. Surface tension is another phenomenon that occurs due to cohesion, those water molecules sticking together. It's like why we can get like a water strider, a bug that kind of just floats on the surface. It's also kind of the reason why it hurts when you do that belly flop. And the idea is those water molecules stick together, and they stick together strong enough that when you like impact it, they got to break that bond. They hold together for a little bit. But then once you're in the water, you can freely move through it, right? You can swim, it moves, it flows. That initial impact, it held together for a moment, and we get kind of that ow effect when you do the belly flop. Because on the surface, they're more attracted to one another. Surface tension is a form of cohesion. Capillary action is a form of adhesion. Different size tubes will pull up different columns of water, different heights. And it has to do with the attractive or the adhesion between water and the container. So if you take like a straw and you dip it in your soda and you pull it out, not putting your finger over the end, but you just stick the straw, put it in, pull it out, you get that little plug. That's capillary action. That's that water being attracted to and being pulled up the straw. The smaller that tube, the higher it goes, and that's how the leaves on the tree trunks or on the branches of a tree get watered. They get pulled through the roots, up through these tiny little tubes to the leaves through capillary action. Okay, but that's kind of the idea of the same capillary action, the meniscus, and when we look at a graduated cylinder, they pull up the sides of a graduated cylinder so you get that dip. That's because of that attractive properties. This is just kind of some general information. A solution is when we take a liquid and we dissolve something in it. Water is referred to often as the universal solvent. The solvent is the liquid that is doing the dissolving, where the salt is the thing that gets dissolved. So the object that's being dissolved. So salt water is a solution. It's a mixture of liquid and something dissolved in it. In this case, it's salt. So the salt is the solute, it's the thing that got dissolved, and water is the liquid that dissolved the salt. Okay? So Kool-Aid is a solution, water is the solvent, the Kool-Aid powder, sugar or whatever, is the solute. And we talk about water being a universal solvent because it dissolves a lot of things. Not everything, but a lot of things. Water is a polar substance. Polar substances will dissolve other polar substances. Polar substances have a charge to them. So polar substances, like water, will also dissolve ionic substances, which have a charge. Salt, table salt, sodium chloride, is an ionic substance. They're ionic bonds holding them together. They're charged particles. So water will dissolve ionic particles and they will dissolve other polar molecules. Polar dissolves polar, polar dissolves ionic, but polar and nonpolar don't mix. Example, oil and water. Oil and water do not mix together. One is polar, one is not. So if you're cooking some cake, you're making some brownies, and you get some vegetable oil on your hand, you go to wash your hands. If you just use water, the vegetable oil is still on your hands, because those two substances didn't mix to flush it off. We have to use some soap, which is called, it has some properties that basically dissolve the oil first and then it tracks to the water and flushes it off. It's called saponification. I think saponification is that. I think so. I don't think it's the making of soap. I think it's that, what I just described. But it surrounds the water droplets because it has both ends up. Okay, so water dissolves a lot, but not everything. That's the idea why they call it the universal solvent. So water has some unique properties. I'm setting up a demo, fingers crossed that it works overnight, that I'm going to try to show you about water and one of the properties. And I needed the help of the tech ed department because I needed some wrenches. And I talked to two tech ed teachers and I was talking about trying to freeze some water in a pipe. And they're like, oh, that water's a weird one. Yes, it is. That's exactly why we're going to talk about it. But when water freezes, it does something different than most molecules do, which is important for life, and it's a good thing that they do. So, today, we have 7 stations that we're going to go through, and we are going to do. The 7 different stations, you will get to some of them today. You will not get to all of them today, and that's okay. We'll have some time tomorrow for you to do some more of them. You're going to go around the room. There's a piece of blue laminated paper, and it has some instructions on what to do at that particular station. Make some observations, answer the questions. On that packet, there's some spaces for you to answer some questions. Once you answer those questions at that station, you're done at that station, you can rotate to one of the other six other stations that are available. It's going to be on your own, move around the room. Follow the instructions, don't be destructive, things like that. I have some demonstrations we're going to set up. And I'm going to set one of them up right now, but I have to grab one more thing from the back room, so I will be right back. Station number 8. So find station number 8 in your water exploratorium packet. Station number 8. So station number 8 in the water exploratorium says your instructor will place some water in a 1,000 ml graduated cylinder. So I did, okay? And then what I'm going to do is I'm going to put some ice in it, and we're going to make some observations. And then, tomorrow, we're going to make another observation. So we got to get this one set up. So, I have some liquid water. It's right around 600 mils, but you don't care about that yet, because we're going to add ice. A says observe. Is the ice resting on the surface, or is it resting on the bottom, or is it floating freely? Floating freely. 8A, floating freely. Should answer that one. Okay? So one of the questions, 8B, says, what is the level of water? So what I'm going to try to do is I'm going to try to push as much of this ice kind of in the water as we can, and then I'm going to make a reading. I try to push this water down, or as much of the ice down as I kind of can. 960. Okay, the volume reading for 8B is 960 milliliters. 960 milliliters. 960 milliliters. You're going to make a prediction. We're going to let this ice melt overnight. I'm going to cover it with parafilm, which is kind of like press and seal or Glad press and seal. It's a way that we can kind of seal it. Why do you think we want to seal the surface? Why do you think we were doing this?
So it doesn't evaporate.
Right, so we don't evaporate. So the idea is the amount of water that we have tomorrow is not due to any change, it was just from the ice melting and not any evaporation. So we said 900, I'm going to write that here, 960 milliliters, and this is what, class 5, 6? Okay. We're going to let it sit overnight. So you, for 8C, are supposed to predict what do you think the level will be tomorrow. And your choices are really, do you think the water is going to be higher than 960? Do you think it's going to be less than 960? Or do you think it's going to be 960? Okay, so that's for you to make that prediction. The other 7 stations that I have around the room, there are instructions once you get there. Just read it, follow the instruction, answer the questions on the Exploratorium packet. You're going to get probably through 3-ish of them today, would be my prediction. Maybe you'll get through 2. We can play it by ear. We'll have some time tomorrow, and that's okay. Couple things. That station number, I think that's 6, thank you. Number 6, there's 2 different liquids. It does say that the liquids are supposed to be the same height. Second period, one of the containers, the red container of rubbing alcohol got spilled. So they aren't the same height, and I know that. And it's okay, because it talks about putting them in and then pulling the pipe. These are glass, be aware of that. These are glass. And if you leave them in like this, the likelihood of them getting bumped and broken is high. So when you pick these up, they're going to drip, and you're supposed to let them drip. You can just kind of keep it over the paper towel, so if it drips on there. And you're just going to make some observations on there, but leave them sitting on the paper towel. Don't leave them in the container. That station, there is an rubbing alcohol that I put a petri dish just to help try to eliminate some of the evaporation. This one, there's some wax paper and some paper towel slices. It talks about a metal spoon. We'll use this. The wax paper, I do have some more wax paper. This one's pretty easy just to kind of dry off quick. The paper towel, I'll get some more of those because we're definitely going to not be able to reuse those. One word of warning is when you get to station number 3 right here, and they do kind of go out of order because I needed an outlet. This one deals with some warm water. This is a petri dish. The petri dish is on a beaker on a hot plate. This also has ice water. And you're going to go through and you're going to put some, this is called a wash glass, on your balance. This is hot water. Okay? It could burn someone. It's near boiling. Now, what happens is if you take this and if you turn it over, did you see how that squirted? Notice how I made sure it wasn't going to squirt at anyone, because this is hot water. Okay? It might squirt. If you keep it like this, it shouldn't be too bad. Okay? It did dribble, but once it kind of gets past that, then it's just drip, 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 drip onto the watch glass. Be mindful that the hot water could squirt, so just be careful where you hold it until it kind of, if it is going to squirt, it kind of do it right away, and then we're good, and then you can do your 20 drips. Don't squirt the hot water on the hot plate. It's going to sizzle there. I told you what's going to happen. Ice water. I counted last hour. 2, 3, 4, 5. 20. There are 20 of these. There are 20. I just counted them. There are 20 of these water molecules. Okay? So at the end of the hour, there's going to be 20 because none of them are going to evaporate into a pocket.
One of them
Okay? Okay? There are 20. And I just counted them. There are 20, and there's going to be 20 at the end of the hour. So, other than that, I think the stations are pretty self-explanatory. If you happen to be at one of the lab stations, you're probably just going to want to put your stuff off to the side. If your desk is really close to a lab station, we might be sliding your desk over slightly to kind of make it a little easier to get to those lab stations. You're rotating on your own. If you have questions, let me know, but read the blue sheets. We'll get through a couple. We'll finish it up tomorrow.